Hello dear students, welcome to mathematics class. So in the last class we have discussed the necessary condition for the function to be analytic, and now let us discuss the sufficient condition for analytic. So in necessary condition it is given that the function is analytic, then we have proved that it satisfies the CR equations. But here it is in reverse order, means given that CR equations are satisfied by the function f of z, then we need to prove that f of z is analytic. So here it is the statement of the necessary and sufficient condition for the function f of z to be analytic. Now the statement for a function f of z, if dou u by dou x, dou u by dou y, dou v by dou x and dou v by dou y exist as continuous first order partial derivatives which satisfy the CR equations in a region R, then it is sufficient for f of z to be analytic. Means all the four partial derivatives are exist and they are continuous, then and also CR equations satisfied by those four partial derivatives, then f of z is analytic. So we know that analytic means the function is defined and differentiable at each point in the region R or in the domain D. So therefore by using that definition, here we need to prove that f of z is analytic. Means for a function f of z to be analytic, or the function f of z is analytic whenever f dash of z exists at each point in the region R. So therefore here also we need to prove that f dash of z exists. So now let us prove this one. Given dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y are exist and continuous. And dou u by dou x equal to dou v by dou y, consider this as first equation, and dou u by dou y is equal to minus dou v by dou x, it is the second equation. Means these first and second equation represents the CR equations. Since it is given that the four partial derivatives satisfy CR equations, hence we can consider these two equations. And here we need to show that f of z is analytic. It means f of z is differentiable, that is f dash of z exists at each point in a region R. So here we need to prove that f dash of z exists. So f dash of z is equal to limit as delta z tends to 0, f of z plus delta z minus f of z divided by delta z. We know that f of z is equal to u of x comma y plus I into v of x comma y, and consider this as the third equation, and f of z plus delta z is equal to what? U of x plus delta x, y plus delta y plus I into v of x plus delta x comma y plus delta y. So, as in the necessary condition, we have considered f of z and f of z plus delta z. In the similar way, here also we are considering those terms, and it is the fourth equation. Now, to prove f dash of z exists, we are going to use the Taylor's theorem for function of two variables. So, let us write the statement of the Taylor's theorem. So, Taylor's theorem for function of two variables, for the function of two variables. So, therefore, the statement is f of x plus h comma y plus k is equal to f of x comma y plus h into dou f by dou x plus k into dou f by dou y plus and so on. So, here it is the function in two variables f of x y plus next first order partial derivatives, and the next term will be second order partial derivatives, third order and so on up to infinity. So, here it is infinite series, the Taylor's series for function of two variables. So, therefore, here in the given function, that is f of z, we have two parts, that u of x comma y and v of x comma y. So, they are also functions of two variables since they are expressed as x, y, right. So, therefore, we can apply this statement for that u of x comma y and v of x comma y. So, while writing those expressions, we are not considering the higher order derivatives, because in the statement it is given that only first order partial derivatives are exist and they are continuous. We do not know about the second and third order and higher order derivatives. So, therefore, we are ignoring those higher order derivatives. So, this statement is important, that is f of x plus h comma y plus k equal to f of x y plus h means increment in x and k is increment in y. So, now u of x plus delta x comma y plus delta y is equal to. So, by using the Taylor's theorem, we are writing this expression, that is u of x comma y plus delta x into dou u by dou x plus delta y into dou u by dou x. Sorry, dou u by dou y, and it is fifth equation. So, in the Taylor's theorem, put h equal to delta x, y equal to delta y and f equal to u, that is dou f by dou x and dou f by dou y is there. So, therefore, here we have written dou u by dou x and dou u by dou y. Then v of x plus delta x comma y plus delta y is equal to v of x comma y plus delta x into dou v by dou x plus delta y into dou v by dou y, and it is sixth equation. Now substitute equations 5 and 6 in 4. Then f of z plus delta z is equal to u of x comma y plus delta x into dou u by dou x plus delta y into dou u by dou y plus I into, because it is the real part, u of x comma y plus I into v of x comma y, that is v of xy plus delta x into dou v by dou x plus delta y into dou v by dou y. It is equal to u of x comma y plus delta x into dou u by dou x plus delta y into dou u by dou y, and now multiply by I, that is I into v of x comma y plus I into delta x dou v by dou x plus I delta y dou v by dou y. Now it is equal to, we know that f of z is u of x comma y plus I into v of x comma y. So therefore u of x comma y plus, here we have I into v of x comma y, it is nothing but f of z plus, so in these two terms we can take delta x common, so therefore delta x into dou u by dou x plus I into dou v by dou x plus, and remaining two terms delta y dou u by dou y and I delta y dou v by dou y, delta y is common, then remaining dou u by dou y plus I into dou v by dou y. Now it is equal to f of z plus delta x into dou u by dou x plus I into dou v by dou x plus delta y. So we know that the CR equations are satisfied by the 4 partial derivatives, right? So now we are going to use those conditions. So dou u by dou y is given by minus dou v by dou x plus I into dou v by dou y is equal to dou u by dou x. We are using CR equations in the second part, which means in the multiple of delta y, because we are reducing this term to this one. So therefore we are using the that CR equations. Now f of z plus delta z, now shifting this f of z to LHS, that becomes minus f of z is equal to delta x into dou u by dou x plus I into dou v by dou x plus, let us take I common, because in this part the coefficient of dou u by dou x is 1, but here it is I, so therefore that we are taking that I outside, then that becomes I into delta y, remaining dou u by dou x here minus 1 by I into dou v by dou x, because there is no I means we need to divide by I, then it is equal to delta x into dou u by dou x plus I into dou v by dou x plus I into delta y dou u by dou x. Here we know that 1 by I is minus I. So minus into minus becomes plus I into dou v by dou x, right? So now these two terms are one and the same, then we can take that as the common term. So therefore dou u by dou x plus I into dou v by dou x is common, remaining delta x plus I delta y. So what is that delta x plus I delta y? That is nothing but delta z, because z equal to x plus iy, then delta z means increment in z. So if z is increasing means both x and y are increasing. So therefore dou u by dou x plus I into dou v by dou x into delta z, that is equal to f of z plus delta z minus f of z. So now rearranging this term, we got f of z plus delta z minus f of z divided by delta z is equal to dou u by dou x plus I into dou v by dou x. Now applying the limit on LHS, now limit as delta z tends to 0, f of z plus delta z minus f of z divided by delta z is equal to dou u by dou x plus I into dou v by dou x. So by using the definition of f dash of x, so this term can be written as f dash of z equal to dou u by dou x plus I into dou v by dou x. So here this formula is very important because we are going to use the same formula while solving the examples. So f dash of z means the differentiation of a function of a complex variable f of z is given by dou u by dou x plus I into dou v by dou x. So here since it is given that dou u by dou x and dou v by dou x exist, because in the statement only it is given that here these four partial derivatives exist. So among these four we have dou u by dou x and dou v by dou x, right? So therefore these two partial derivatives exist, means, and sum of these two is equal to what? F dash of z. So therefore f dash of z also exist. So if f dash of z exists, then what we can say? It implies that f of z is differentiable. If the function is differentiable, then we can say that that is analytic. So therefore we have proved here, when the CR equations are satisfied by the partial derivatives, then the function is analytic in that region. So here the necessary and sufficient condition is very important and is fixed in the semester exams.